When you pick up a rock, you assume you're holding something solid, something real, something made of stuff. But modern physics tells us something deeply strange about that rock. That if you could zoom in far enough, past the crystals, past the molecules, past the atoms, past the nucleus, past the quarks themselves, you would find almost nothing. Not emptiness exactly. Something stranger than that. You would find energy moving in patterns, fields looping back on themselves, motion frozen into the appearance of matter. The closer we look at the physical world, the less solid it becomes. This is not a metaphor or a philosophical position. It is the result of 2,500 years of increasingly precise experiments, each one stripping away another layer of the illusion that matter is fundamentally made of stuff. What we find instead, at every level of investigation, is the same answer: energy, fields, motion. This is the story of how we got there. It begins not in a laboratory, but in the ancient world, with two strange stones. The first was a heavy black rock, found near a town called Magnesia, in what is now Turkey. This stone had a peculiar property. Bring it close to iron, and the iron would be pulled toward it without any visible connection. No touch, no thread, no mechanism. The iron simply moved. The force reached across empty space and acted. The second stone was amber fossilized tree resin, millions of years old. When rubbed with animal fur, amber would attract lightweight objects, feathers, dust, thin strips of papyrus. Again, no visible connection, a force acting across a gap. These two phenomena sat at the heart of one of the deepest puzzles in the history of science. Not just what are these forces, but how can any force act at a distance? How can something reach across empty space and push or pull without touching? The ancient Greeks, who documented both effects carefully, had only one analogy available to explain invisible influences that acted at a distance: life itself. They reasoned that these stones must have souls. They must want to move things. The rock reaches out and pulls the iron because it desires connection. This sounds absurd today, but at the time, it was the most sophisticated explanation available. The idea of a soul was not purely religious. For the Greeks, the soul was the organizing principle behind any movement. Rocks fell because they were drawn to their natural place. Animals moved because they had animal souls. And the magnetic stone, they concluded, must have a kind of mineral soul that reached out toward iron. This animistic explanation held for a while, but it was unsatisfying to thinkers who preferred mechanical explanations. If there was no soul, then what was actually happening? What was the physical mechanism by which one object exerted force on another across empty space? A new analogy emerged: smell. This might seem even stranger than the soul explanation, but it had a compelling logic. Smell was the only natural phenomenon people could readily identify in which an invisible effect traveled through empty space and caused a reaction at a distance. You could not see scent particles, you could not touch them, but they reached you from across the room and triggered a response. In some sense, smell demonstrated that invisible influences could travel through air and act on matter. And so theorists imagined that the magnetic stone emitted tiny, invisible particles. These particles had a shape like keys, in one version of the theory. The iron had tiny pores whose shape exactly matched these key-shaped particles. The particles would enter the pores and somehow tug the iron along behind them. Materials like wood had differently shaped pores, so the magnetic particles bounced off without effect. It is easy to dismiss this as primitive fantasy, but notice what the theory was actually trying to do. It was attempting to reduce an invisible force to a mechanical process. It was asking, what is the underlying physical mechanism? That impulse is exactly right. The answer just turned out to be far stranger than anyone imagined. The smell analogy gave way to another: suction. In ancient medicine, cupping was a common treatment. A glass vessel was heated and placed on the skin. As the air inside cooled and contracted, it created a partial vacuum that pulled the skin upward. The effect was real. A force appeared to reach inside the cup and draw the skin toward it. Some thinkers proposed that magnetic stones worked the same way. They created tiny, invisible regions of low pressure around nearby objects, sucking them closer. The stone pulled the iron not by emitting particles, but by creating a void that nature then filled. Again, wrong in detail, but not in spirit. The thinkers asking these questions were serious people trying to understand a real phenomenon using the conceptual tools they had. Each analogy captured something about the behavior of the force, its reach, its selectivity, its directionality, even when it failed to identify the actual mechanism. For centuries, the dominant explanation across many cultures was that these invisible forces were a kind of wind. In Chinese natural philosophy, the concept of qi, sometimes written qi, referred to a kind of breath or vital energy that permeated the world. The earth itself breathed this force, and it influenced compasses, aligned mountains, determined the flow of rivers. The magnetic force was qi in motion. This wind explanation had a certain elegance. Wind was invisible. Wind traveled in all directions. Wind exerted force without contact. And wind was everywhere, just as the magnetic field appeared to be. But wind could be felt. Wind could be blocked. Wind could be blown away by other winds. And experiments, when they came, showed that the magnetic force could do none of these things. The era of real progress began in the 1600s, when natural philosophers stopped accepting inherited explanations and began designing experiments to test them. William Gilbert was a physician serving Queen Elizabeth I of England. He was also deeply skeptical of every existing theory of magnetism and electricity, and he had the resources and the curiosity to actually test them. He began with the most basic questions. Can you block magnetism? Can you blow it away? Does it depend on what the intervening material is? He placed magnets behind sheets of paper. He placed them behind glass. He submerged them in water. In every case, the force passed through completely unchanged. He set up wind sources beside magnets to see if the force could be displaced. It could not. He tested every kind of blocking material he could find. The results were consistent. The magnetic force was not a wind, because wind could be blocked and this could not. It was not a stream of particles, because no emission could be detected and no substance was consumed. And it could not be explained by suction, because suction required a medium to create a pressure differential, and the force worked in every medium, including vacuum conditions available to him. Gilbert concluded that the force was something entirely different from all the analogies that had come before. He described it as a sphere of power extending outward in all directions from the stone, with the same shape at every scale. He called it an orb of virtue. This was actually a major conceptual advance. Gilbert was proposing what we would now call a field, a region of space that has a property at every point, a property that causes other objects to experience a force when they enter the region. He did not have the mathematics to formalize this, but the intuition was correct. Then he turned his attention to amber, and he found something puzzling. The amber force, which he named electricus from the Greek word for amber, behaved very differently from magnetism. It could be blocked by a single sheet of paper. Wind could deflect it. Different materials responded to it differently. While magnetism was fairly indiscriminate, the amber force seemed to select for lightweight objects, rather than specifically for iron. Gilbert concluded these were two completely distinct phenomena. He had identified both, named one of them electricity, and confirmed that neither was wind or scent or soul. But their deeper nature remained unknown. For another century, electricity was studied as a strange property of certain materials when rubbed. Then came an accidental discovery that changed everything. In 1729, an English scientist named Stephen Gray was exploring how far the electric attraction could reach. He was experimenting with charged objects, things rubbed with fur, to build up the mysterious amber force and testing their ability to attract lightweight items. Gray set up a simple experiment. He placed a small, lightweight ball at some distance from a charged object and connected them with a wire. And he found that when he charged the object at one end, the force appeared to travel down the wire and affect the ball at the other end. The force moved. It traveled through a conductor like water flowing through a pipe. This was incompatible with the smell or scent model. Smells did not flow through wires, but fluids could. And so a new analogy emerged. Electricity was an invisible, weightless fluid that flowed through conducting materials from regions of high concentration to regions of low concentration. Lightning was a massive sudden flow of this fluid. The amber effect when rubbing built up a pool of it. Running it through a wire distributed it. The fluid model was wrong in detail, but enormously productive. It explained many observed behaviors of electric charge. It correctly predicted that charge was conserved. What flowed out of one place flowed into another. It suggested that conductors were materials the fluid could pass through, and insulators were materials it could not. By the early 1800s, the electric fluid model was the dominant explanation. Electricity was a flow, and magnetism was a field. They were still seen as completely separate forces. That changed on an April evening in 1820, in a classroom in Copenhagen. Hans Christian Ørsted was a Danish professor of physics, and while preparing a lecture demonstration on electric current, he happened to have a compass needle sitting on a nearby table. When he connected a wire to a battery and current began to flow, the compass needle twitched. He noticed, and he spent the next few months carefully investigating what he had seen. The result was definitive. A flowing electric current created a magnetic force around the wire, not pointing outward from the wire like a spoke from a wheel, but circling around the wire like a whirlpool. The magnetic field wrapped around the current in continuous circles, forming a vortex pattern in space. This was the first demonstration that electricity and magnetism were connected. The two forces were not independent. One could create the other. The scientific world was electrified by this result, and no one pursued it more obsessively than Michael Faraday, an English scientist who had worked his way up from bookbinding apprentice to become one of the most talented experimentalists in history. Faraday had almost no formal mathematical training, but he had an extraordinary physical intuition and an almost superhuman capacity for careful observation. Ørsted had shown that a moving charge creates a magnetic field. Faraday immediately asked the obvious question: does the reverse work? Does a changing magnetic field create an electric current? For 10 years, he tried to find out. The results were confusing and inconsistent. Sometimes he got a signal, sometimes he did not. But gradually he identified the key. It was not a static magnetic field that produced current. It was a changing one. In 1831, Faraday performed the definitive experiment. He shook a magnet near a wire, just moved it back and forth, and measured an electric current appearing in the wire at the precise moments of movement. No battery, no chemical reaction, no contact between magnet and wire, just motion. And from that motion, electricity. This discovery, electromagnetic induction, is the basis of every electrical generator ever built. Every power station on Earth works by spinning magnets near wires, or wires near magnets, in exactly the manner Faraday demonstrated. The flow of charge that powers civilization is created by the simple act of changing a magnetic field. But Faraday drew a deeper conclusion. If a changing magnetic field creates an electric current in a wire, what happens in empty space with no wire? Does the electric force appear there too, just with no conductor to carry it? Faraday thought the answer had to be yes. He imagined lines of force filling all of space, visible threads, representing the direction and strength of the electric and magnetic forces at every point. These lines were not just a visualization tool. He believed they were physically real. And if the electric force was a field, a property of space itself, then so was the magnetic force. Not a fluid, not a stream of particles, not a wind. Both forces were fields, distortions in the fabric of space. This set the stage for the greatest theoretical achievement of the 19th century. James Clerk Maxwell was a Scottish mathematician and physicist who read Faraday's work and recognized that the physical intuitions Faraday had developed through decades of experiments needed to be formalized in mathematics. Faraday himself had neither the training nor the inclination for mathematical physics. But Maxwell saw that the lines of force Faraday described could be encoded in equations. Maxwell set out to do this, but he faced a deeper challenge. If the electric and magnetic fields could influence each other, a changing magnetic field creating an electric force, and a changing electric force creating a magnetic field, then it should be possible for the two to create each other continuously in a chain. A changing electric field creates a changing magnetic field, which creates a changing electric field, which creates a changing magnetic field, and so on, propagating outward through space. But what was the speed of this propagation? When you move a magnet, how long does it take for a distant compass to feel the effect? Does the change travel instantaneously? Or does it take time to cross the space? To answer this, Maxwell needed to understand the physical properties of the electromagnetic field. He invented an elaborate mechanical model to develop his intuitions. He imagined all of space filled with tiny invisible spinning objects. Think of cylindrical rollers or drums, packed tightly together. To allow them to spin freely without grinding against each other, he placed tiny ball bearings in every gap between them. When one roller was set spinning, the ball bearings transferred that rotation to adjacent rollers, which transferred it to rollers further away, and so on. A disturbance would propagate through this mechanical medium as a wave. The wave would have a speed determined by two properties of the medium, its stiffness and its density. This is a general principle of wave physics. Sound waves travel faster through steel than through air because steel is stiffer. Waves travel faster through a light spring than through a heavy one. The speed is always the square root of the stiffness divided by the density. Maxwell now needed values for the stiffness and density of the electromagnetic field. Stiffness corresponded to the electric restoring force, how strongly the electric field pushed back when disturbed. Density corresponded to the magnetic inertia, how much the magnetic field resisted being changed once established. Both of these quantities had been measured in the laboratory through careful experiments with capacitors and inductors. Maxwell plugged in the numbers. The speed came out to 300 million meters per second. This was not a surprising number in a vacuum. It was a profoundly astonishing one, because the speed of light had already been measured, and it was 300 million meters per second. Within the uncertainty of the measurements at the time, these two numbers were identical. The implication was inescapable. Light is not a separate thing from electricity and magnetism. Light is a wave in the electromagnetic field. When an electric charge oscillates, it creates an oscillating electric field, which creates an oscillating magnetic field, which propagates outward through space at the speed of light, because it literally is light. Electricity and magnetism were not two forces. They were two aspects of a single force. Maxwell called it the electromagnetic field, and the equations he wrote to describe it have become known as Maxwell's equations, four elegant relationships that completely describe the behavior of electricity, magnetism, and light. The experimental confirmation came in 1887, 11 years after Maxwell published his equations, and 5 years after his death at 48. Heinrich Hertz set up an experiment in his laboratory in Karlsruhe. He placed two metal rods with a small gap between them connected to a source of high-frequency alternating current. When the current oscillated fast enough, a spark would jump across the gap, creating a rapid oscillation of charge, and therefore, according to Maxwell, an outgoing wave of electromagnetic radiation. Several meters away, he placed a second gap with no electrical connection to the first, and when the first gap sparked, the second one sparked too. The electromagnetic wave, generated by the oscillating charge at the source, traveled through the air and induced a new oscillation at the receiver, which was strong enough to jump the gap. There was no wire connecting them. The wave was real. Radio had been invented, though Hertz did not know it yet. This settled the question of whether electromagnetic fields were physical realities or just mathematical bookkeeping devices. They were real. They propagated through space. They carried energy. They could interact with matter at a distance. Now the question shifted. If light is a wave in a real physical field, and if matter is made of atoms and electrons and other charged particles, then maybe matter itself is not as separate from light as it appears. This thought occurred to Lord Kelvin, one of the most celebrated physicists of the 19th century, shortly after Maxwell's work began to spread. Kelvin had been watching demonstrations of smoke rings, vortices of air, that form compact, self-sustaining loops. A skilled demonstrator could fire rings across a room. They would maintain their shape, spin, and momentum. Two rings approaching each other at an angle would interact in complex ways. They were stable structures. A mathematician named Hermann von Helmholtz had proven something remarkable about vortices in 1858. In an ideal fluid one, with no viscosity and no friction, vortex rings were perfectly stable objects. They could not spontaneously appear or disappear. They could change shape and interact, but the total vortex content of the fluid was conserved. If you had 10 vortex rings, you would always have 10 vortex rings. They could be deformed, combined, or split, but they could not be created or destroyed. This sounded, to Lord Kelvin, very much like atoms. Atoms could not be created or destroyed by ordinary chemistry. Every atom that went into a reaction came out of it, sometimes rearranged into different molecules, but always conserved. And at the time, no one had any idea what atoms actually were. The kinetic theory of gases was treating them as tiny, hard spheres, but there was no reason to think that model was literally true. Kelvin proposed in 1867 that atoms might be vortex rings in the electromagnetic field. If Maxwell was right that the field filled all of space, and if Helmholtz was right that vortex rings in an ideal fluid were perfectly stable, then maybe atoms were not tiny hard balls, but stable patterns of motion in the electromagnetic field itself. The idea was ahead of its time by about a century. It was eventually abandoned because the mathematics did not work out. The properties of classical vortex rings did not match the observed properties of atoms. But the intuition turned out to be pointing in exactly the right direction. Decades later, two physicists named John Williamson and Martin van der Mark asked a more specific version of the same question. What happens if you take a single photon, a single quantum of light, the smallest possible unit of electromagnetic radiation, and bend it into a closed loop? Mathematically, this is a well-defined question. A photon has energy, momentum, and spin. If it circulates in a loop, what properties does the resulting structure have? The answer, they found, was remarkable. A looped photon has an electric charge. It has a magnetic field. It has a spin of 1/2. It has a mass that equals its energy divided by the speed of light squared. In other words, it has all the properties of an electron. This does not mean the electron definitely is a looped photon. It means that if you take light and force it into a closed loop, you get something that looks exactly like an electron by every measurable property. Mass, charge, spin, magnetic moment, all of it falls out of the geometry. And the mass is not a coincidence. It requires an explanation. When light travels in a straight line, it has energy but no rest mass. But when that energy is confined, forced to circulate in a loop, unable to escape, it creates something that resists being accelerated. Push on it, and it pushes back. That resistance is exactly what we call mass. The equation E equals mc squared, written by Einstein in 1905, says precisely this. Energy and mass are the same thing in different forms. Mass is densely confined energy. A rock is not a pile of stuff. It is a collection of energy trapped in patterns. This interpretation makes sense of experiments that otherwise seem almost magical. In 1933, physicists discovered something that had been theoretically predicted, but was still startling to witness. When a high-energy photon, a gamma ray, which is just very high-frequency light, passes near an atomic nucleus, it can spontaneously disappear. In its place, two particles appear from nothing, an electron and a positron, which is an electron with the opposite electric charge. The photon has become matter, and the reverse works too. Bring an electron and a positron together, and they annihilate. Both particles disappear and are replaced by two gamma-ray photons. Matter has become light. This process pair, production and annihilation, happens constantly in high-energy physics experiments. It is the basis of positron emission tomography, used in medical imaging. It is observed in cosmic ray interactions in the upper atmosphere. It is routine physics. But think about what it means. You can take light and convert it into particles. You can take particles and convert them back into light. If the particle is a pattern of trapped light and the photon is free-traveling light, then matter is just light that has been caught in a loop. The rock in your hand and the sunlight falling on it are made of the same thing in different configurations. By the early 20th century, experiments had revealed the internal structure of atoms in detail that would have seemed fantastical to Gilbert or Faraday. In 1911, Ernest Rutherford fired particles at a thin gold foil and found that most passed straight through, but a few bounced back sharply. This meant the atom was not a uniform blob of matter, but was mostly empty space with a tiny dense nucleus at the center. The nucleus was roughly 100,000 times smaller than the atom itself, which means that if the nucleus were the size of a marble, the atom as a whole would be roughly the size of a football stadium. The electron orbits somewhere in the vast empty space between. This is the atom, as most people learn about it in school. But it understates how strange the atom actually is. The nucleus contains protons and neutrons, packed tightly together. For a while, protons and neutrons were considered fundamental, the smallest pieces of matter. But in the 1960s, physicists began firing electrons at protons with such force that the electrons were deflected by hard, tiny objects inside the proton. These were quarks. 3 quarks, held together by a completely different force than electromagnetism, make up each proton and neutron. And when physicists tried to calculate where the mass of the proton was coming from, they found something unexpected. The 3 quarks that compose a proton account for only about 1% of the proton's mass. The rest 99% comes from the energy of the fields holding the quarks together. The strong nuclear force, which confines quarks inside protons and neutrons, creates an intense field between them, whose energy is itself the source of most of the mass. In other words, even the most solid-seeming part of the atom, the dense little nucleus, is not primarily made of stuff. It is made of energy and motion, of fields, of the same fundamental reality as light, just organized differently. The strong force has another deeply strange property. When you try to pull two quarks apart, the force between them does not diminish with distance the way gravity or electromagnetism does. Instead, it stays roughly constant. The further you pull, the more energy you put into the field between them. And if you pull hard enough, at some point the field has accumulated so much energy that it can spontaneously create a new quark-antiquark pair from that energy. The tube of force snaps, and you end up with more particles than you started with. You cannot isolate a quark. Every attempt to pull one out of a proton results in new particles being created from the energy of the attempt. Matter bootstraps itself. The field becomes the particle. This behavior, the field collapsing into a tube, the tube snapping into new particles, is another version of the same pattern we have seen at every level of investigation. Fields creating stable structures, energy becoming matter through geometry. The question of whether all the fundamental forces are ultimately the same field in different configurations is one of the central open questions in physics. Maxwell unified electricity and magnetism. A century later, Steven Weinberg, Abdus Salam, and Sheldon Glashow unified electromagnetism with the weak nuclear force, the force responsible for certain types of radioactive decay. Their electroweak theory was confirmed by experiments in the 1980s and earned them the Nobel Prize. Physicists have spent decades attempting to incorporate the strong force into the same framework, and further to include gravity. These attempts are ongoing. String theory, loop quantum gravity, and various other approaches all attempt to find a single underlying description from which all the known forces emerge as different aspects of the same thing. Whether or not a unified theory exists, and whether or not we will ever find it, the pattern at every scale we have investigated so far is the same. The deeper we look, the less we find matter, and the more we find fields, energy, and motion. Consider what we know about the electron specifically. The electron is, as far as we can tell, a point particle. It has no measurable size. It is not made of smaller components that we have detected, and yet it has a precise electric charge, a precise mass, a precise spin, and a precise magnetic moment. These properties are exactly what you would predict if the electron were a pattern in the electromagnetic field, a stable configuration of energy with a particular geometry. In quantum electrodynamics, the quantum theory of the electromagnetic field developed in the 1940s by Richard Feynman, Julian Schwinger, and Sine Ichiro Tomonaga, the electron, is described as an excitation of the electron field. There is, in this picture, an electron field that permeates all of space, just as the electromagnetic field does. An electron is not a thing sitting inside the field. An electron is a vibration of the field, a local oscillation in the fabric of reality. The same is true of every other particle in the standard model of particle physics. Quarks are excitations of quark fields. Photons are excitations of the electromagnetic field. The Higgs boson is an excitation of the Higgs field. Every particle, every piece of matter that has ever existed, is a pattern of energy in some underlying field. This is not a poetic interpretation. It is what the mathematics of quantum field theory directly states. The equation describing an electron is not an equation about a tiny ball. It is an equation about a wave in a field. And yet when you measure an electron's position, you find it in one place. It behaves like a particle. It leaves a dot on a detector screen. It can be counted. In that sense, the particle picture is also valid. This wave-particle duality, the fact that quantum objects behave like waves when you do not observe them, and like particles when you do, is one of the deepest and still not fully resolved mysteries of physics. We have the mathematics to predict what will happen with extraordinary precision. We do not have a universally agreed upon story about what is actually going on. But whatever the correct interpretation turns out to be, it is clearly not the case that matter is made of solid stuff. At the deepest level we have probed, we find fields and energy. We find oscillations and patterns. We find geometry creating mass. We find light trapped in configurations that we experience as solid objects. The 2,600-year journey from the Amber Stone to quantum field theory is a story of analogies being replaced by better analogies, each one capturing more of the reality it was trying to describe. The soul gave way to the scent to the fluid to the field to the quantum. At each step, the explanation became less intuitive and more accurate, and the answer we have arrived at is this. There is no stuff at the bottom. There are fields. And in those fields, stable patterns of energy form and persist, some for fractions of a second, some for billions of years. The patterns interact with each other according to precise rules. They exchange energy and momentum and spin. They attract and repel. They create larger patterns of greater and greater complexity: atoms, molecules, crystals, rocks, planets, stars, living organisms capable of wondering what they are made of. Everything you can touch is light that has been caught in a loop. Every force you can feel is the geometry of space, itself pushing back. Every rock is trapped light. The questions that remain are not small ones. We do not know why the fields have the properties they do. Why does the electron have the mass it has? Why do the fundamental constants, the speed of light, the strength of gravity, the charge of the electron, take the values they take? If they were even slightly different, atoms could not form, stars could not burn, life could not exist. Whether this is a coincidence, a consequence of some deeper principle, or an artifact of the fact that we can only exist in a universe that permits our existence, is genuinely unknown. We do not know what dark matter is. Roughly 26% of the energy content of the universe appears to consist of matter that interacts gravitationally, but does not interact electromagnetically. It emits no light and reflects no light. It passes through ordinary matter as if it were not there. Its nature is completely unknown. It may be an undiscovered particle, an unknown field, a modification to our theory of gravity, or something else entirely. We do not have a consistent theory that combines general relativity, Einstein's description of gravity, as the curvature of space-time with quantum mechanics. At the smallest scales and highest energies, both theories apply simultaneously, and their predictions are incompatible. This conflict sits at the edge of our understanding and is possibly the most important unsolved problem in fundamental physics. And we do not fully understand why observation plays the role it does in quantum mechanics. The mathematics tells us that a particle does not have a definite position until it is measured. Before measurement, it exists in a superposition, a combination of all possible positions. The act of measurement appears to select one. What actually happens during that selection, and whether it is a physical process or an artifact of how we set up the theory, remains actively debated among physicists and philosophers of physics. 2,600 years of inquiry have answered the question of what matter is made of in a way that is far stranger than anyone initially suspected. The answer is not atoms. The answer is not particles. The answer is fields and energy and motion. The world is made of light that has learned to stay in one place. And the deeper we look, the more clearly that picture comes into focus. Every experiment, every particle accelerator, every precision measurement has confirmed the same extraordinary fact. At the bottom of reality, there is no bottom. There is only the field and the patterns it makes, and us patterns in the field that have become curious about themselves. To truly appreciate how extraordinary this conclusion is, we need to go back and linger on each step. Because the story of how we discovered that matter is made of trapped light is not just a list of experiments. It is a map of how human understanding actually works. Each generation inherited a framework, pushed it to its limits, found where it broke, and built something better in its place. The progression from soul to field is not a straight line. It is a series of shattering realizations, each one more counterintuitive than the last. Let us begin again, more carefully. When William Gilbert finished his experiments in 1600 and published his great work on magnetism, the first major scientific treatise based on systematic experiment rather than inherited philosophy, he was making a radical, methodological statement. He was saying that the way to understand the world was not to reason from first principles or to accept ancient authority, but to interrogate nature directly, to design tests that could rule out explanations. His sphere of virtue, the field surrounding a magnet, was not just a description, it was a challenge. It said, "Here is something real, now explain it." The challenge went unanswered for more than 2 centuries. In the meantime, the study of electricity developed separately through a series of increasingly bizarre discoveries. By the 1700s, experimenters had learned to build Leyden jars early capacitors that could store large amounts of electric charge and release it suddenly. They staged public demonstrations in which chains of people holding hands would receive simultaneous shocks. They sent sparks across rooms. They killed birds and small animals with electrical discharge. Benjamin Franklin, conducting his famous kite in a thunderstorm experiment around 1752, demonstrated that lightning was an electrical phenomenon, the same force as the static electricity built up by rubbing amber or glass. He invented the lightning rod as a practical application. For the first time, one of the most destructive natural forces could be domesticated. But none of this explained what electricity actually was. The fluid model persisted. Charge was imagined as a fluid that could accumulate on surfaces, flow through conductors, and leap across gaps. Franklin himself contributed to this model, distinguishing between what he called positive and negative charge, based on whether an object had an excess or deficit of the electric fluid. The fluid model predicted correctly that charge was conserved. It correctly explained why a conductor could distribute charge across its surface, but it said nothing about where the fluid came from or what it was made of. Meanwhile, precision measurement was beginning to reveal mathematical patterns in the behavior of both electricity and magnetism. In 1785, Charles Augustin de Coulomb established through careful experiments with a torsion balance that the force between two electric charges fell off with the square of the distance between them, just as Newton had shown that gravity did. The force was weaker by a factor of 4 when the distance doubled, weaker by a factor of 9 when it tripled. This mathematical parallel between electricity and gravity was not lost on physicists. Both forces followed the same inverse square law. Both reached across empty space. Both acted on specific properties of objects' mass for gravity, charge for electricity. Were they perhaps manifestations of the same underlying reality? The question could not be answered yet, but it planted a seed. The French mathematician Siméon Denis Poisson, and later the German mathematician Carl Friedrich Gauss, formalized the mathematics of electric and magnetic fields in the early 1800s. They could write down equations describing how the field behaved at every point in space given a configuration of charges or magnets. The mathematics was precise and powerful. It allowed predictions to be made and tested. But the field was still just mathematics. It was a way of computing the force that would be experienced by any charge placed at a given location. Whether the field was physically real, whether it had existence apart from the charges that created it, and the charges that felt it was not settled. That question was settled by Faraday's experiments and Maxwell's equations together. Faraday's experiments showed that the field had energy. When you push a magnet toward another magnet against the repulsive force, you do work. Where does that energy go? It cannot go into the magnets themselves, because they have not changed internally. It must go into the space between them, into the field. And when the magnets are released, that energy comes back out. The field stores energy and releases it. Something that stores energy is real. Maxwell's equations showed that the field could propagate through space as a wave, carrying that energy with it. A disturbance in one part of the field would travel outward, carrying the energy of the disturbance, and eventually deposit that energy somewhere else. The field was not just a passive description. It was an active carrier of energy through space. And then came the speed calculation. When Maxwell found that the speed of electromagnetic waves was 300 million meters per second, identical to the measured speed of light, the implications were revolutionary. It had been known since the 1600s that light had a finite speed. The Danish astronomer Ole Romer had measured it in 1676 by observing timing discrepancies in the moons of Jupiter. When Earth was moving away from Jupiter in its orbit, the moons appeared to fall slightly behind schedule. When Earth was moving toward Jupiter, they appeared slightly ahead. Romer correctly interpreted this as a light travel time effect. The signal from Jupiter was taking longer to arrive when Earth was farther away. His estimate, about 220,000 kilometers per second, was rough, but he had the right idea. Light took time to travel. Over the following 2 centuries, measurements improved. By the time Maxwell was working, the speed of light was known to be approximately 300 million meters per second. When this number emerged from Maxwell's equations, it told him that light was not a separate phenomenon from electricity and magnetism. Light was an electromagnetic wave, the bright yellow sodium flame, the invisible heat radiation from a warm object, the radio waves from a spark gap, the X-rays from a high-voltage tube. All of these were the same electromagnetic field oscillating at different frequencies. The electromagnetic spectrum, the full range of electromagnetic radiation, from the lowest frequency radio waves to the highest energy gamma rays, is a single phenomenon spanning an enormous range of energies. Visible light occupies a tiny slice of this spectrum, the portion our eyes evolved to detect because the sun emits most of its energy there. But the underlying physics is identical across the entire spectrum. And that physics is this. An oscillating electric charge disturbs the electromagnetic field. That disturbance propagates outward as a coupled wave of oscillating electric and magnetic forces. When it reaches another charged object, it causes that object to oscillate too, transferring energy in the process. This is not a poetic description. Every piece of technology that involves wireless communication, radio, television, cellular phones, satellite navigation, wireless internet, operates on exactly this principle. Maxwell's equations, written in 1865, describe every one of them precisely. Now, back to the central question. If light is a wave in the electromagnetic field, and if charged particles interact with that field, then matter and light are not as separate as they appear. They are two aspects of the same electromagnetic reality. The question is, how waves become particles? How does vibration become structure? The vortex ring model that Kelvin proposed in 1867 was the first serious attempt to answer this. And even though it failed in its original form, the idea that stable patterns in a field could behave like particles that geometry could create mass was exactly right. What Kelvin lacked was quantum mechanics. The equations that govern classical fields do not naturally produce stable discrete objects. A classical electromagnetic field, disturbed at one point, sends out ripples in all directions that gradually dissipate. There is no mechanism in classical electrodynamics for trapping that energy in a stable, localized structure. Quantum mechanics changes everything. In 1900, Max Planck was trying to explain the spectrum of light emitted by a glowing hot object. According to classical physics, the amount of energy emitted should increase without limit at high frequencies. This prediction was not just wrong, it was catastrophically wrong in a way that implied hot objects should emit infinite energy, which is obviously not what happens. This failure was called the ultraviolet catastrophe. Planck found that he could correctly predict the observed spectrum if he made a single strange assumption: that energy could only be emitted or absorbed in discrete chunks, whose size was proportional to the frequency of the radiation. He called these chunks quanta. The proportionality constant is now known as Planck's constant, and it is one of the most fundamental numbers in the universe. 5 years later, Albert Einstein extended this idea. He proposed that light was not just emitted in discrete quanta, but actually traveled in discrete quanta. Light was not merely a wave, it was also a stream of particles, each carrying a discrete amount of energy. He called these particles light quanta, and they are now called photons. Einstein used this idea to explain the photoelectric effect, the fact that light shining on a metal surface can knock electrons off it, but only if the frequency of the light exceeds a certain threshold, regardless of the intensity. Below the threshold, even very bright light did nothing. Above the threshold, even very dim light knocked electrons off immediately. This made no sense if light were purely a wave, but it made perfect sense if light were particles, each carrying a fixed energy proportional to frequency. Only photons above a certain energy threshold had enough energy to knock out an electron. For this work, not for relativity, Einstein received the Nobel Prize in Physics in 1921. But now there was a paradox. Experiments like Young's double-slit experiment, first performed in 1801, clearly showed that light was a wave. It created interference patterns alternating bright and dark bands that could only be explained by waves interfering with each other. A stream of particles would not produce interference patterns. And yet, Einstein's photoelectric effect clearly showed that light was a particle. It interacted with electrons one at a time, in discrete exchanges of energy. How could light be both? This paradox deepened when physicists realized it applied not just to light, but to matter as well. In 1924, the French physicist Louis de Broglie proposed that if light had particle-like properties, perhaps matter had wave-like properties. He derived a simple equation relating the wavelength of a particle to its momentum. Experiments confirmed this almost immediately. Electrons fired at a crystal-produced diffraction patterns the signature of waves. Individual electrons, one at a time, were behaving like waves, spreading through space and interfering with themselves. The resolution of this paradox came in the form of quantum mechanics. In the new theory, developed in the mid-1920s by Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and others, quantum objects do not have definite positions or velocities. Instead, they are described by a mathematical object called a wave function that encodes the probability of finding the object at each possible location. When you observe an electron, when you interact with it in a way that localizes it, the wave function collapses to a definite value. The electron appears at one point. Before observation, it was spread out as a wave of probabilities. This is deeply strange. And 100 years later, physicists and philosophers are still arguing about what it means. But what is not in dispute is the accuracy of the mathematics. Quantum mechanics predicts experimental outcomes with a precision that no other physical theory has ever matched. Its predictions have been confirmed to more than 12 decimal places in some cases. And when you apply quantum mechanics to fields, you get quantum field theory, the framework that unifies quantum mechanics with special relativity and describes all the known fundamental forces, except gravity. In quantum field theory, every particle is an excitation of a field. The photon is an excitation of the electromagnetic field. The electron is an excitation of the electron field. The quarks are excitations of quark fields. And so on for every type of particle in the standard model of particle physics. This is not just a mathematical formalism. It has physical consequences. One consequence is that fields have what is called a vacuum energy. Even when no particles are present, even in empty space with no matter and no radiation, the fields are not quiet. They fluctuate. Quantum uncertainty means that the energy of the field cannot be exactly zero. There are always tiny fluctuations, appearing and disappearing on timescales too short to observe directly. These vacuum fluctuations have measurable effects. The Casimir effect, first predicted in 1948 and confirmed experimentally, arises from this vacuum energy. If you place two flat metal plates very close together in a vacuum, you can measure an attractive force between them that has no classical explanation. The force arises because the vacuum fluctuations between the plates are restricted. Only oscillations that fit between the plates can occur there, while the fluctuations outside the plates are unrestricted. The imbalance in vacuum energy creates a measurable force. This is not a small effect. The Casimir force is large enough to be important in the design of tiny mechanical devices like micro-electromechanical systems. It is a force created by empty space, pushing on objects. The vacuum is not nothing. It is a seething foam of field fluctuations, and it exerts measurable pressure. Another consequence of quantum field theory is the Higgs mechanism, which explains why some particles have mass and others do not. The photon has no rest mass. It always travels at the speed of light and cannot be slowed down. The electron has a very small rest mass. The proton has a mass roughly 1,800 times larger than the electron. The W and Z bosons, which carry the weak nuclear force, have masses roughly 80 to 90 times the mass of the proton. Why do these particles have the masses they do? The answer, according to the standard model, involves the Higgs field. The Higgs field permeates all of space, and particles acquire mass by interacting with it. A particle that interacts strongly with the Higgs field acquires a large mass. A particle that interacts weakly acquires a small mass. A particle that does not interact at all, like the photon, has no rest mass. The Higgs boson, discovered at the Large Hadron Collider at CERN in 2012, is an excitation of the Higgs field, a ripple in it. Just as the photon is a ripple in the electromagnetic field, its discovery confirmed that the Higgs field is real. So now we have an even more complete picture. Not only is the mass of composite objects like protons mostly the energy of the fields inside them, even the mass of elementary particles like electrons comes from their interaction with a field, the Higgs field. Mass, in the modern picture, is never a property of stuff. It is always a consequence of how energy is organized and how fields interact. The rock on a table is not a pile of hard little balls sitting in empty space. It is an enormously complex pattern of electromagnetic, strong, weak, and Higgs field excitations, all interacting according to precise rules, all ultimately reducible to fields that fill all of space and whose fluctuations give rise to everything we experience as solid and real. The table the rock sits on is made of the same fields. So is the air above the table. So is the floor beneath it. So is the planet. So are you. Every atom, every molecule, every structure that has ever existed in the physical universe is a pattern in the fields. And the fields themselves, what are they? This is where physics currently stands at its frontier. The fields are described by the mathematics of quantum field theory with extraordinary precision. But what they are, in some deeper ontological sense, what they are made of, whether they exist in space-time or whether space-time emerges from them, what the nature of the wave function actually is, these questions remain open. Some physicists think the fields are the fundamental reality, and that matter and space-time both emerge from them. Others think that quantum mechanics and general relativity point toward a deeper theory, in which neither spacetime nor fields are fundamental, in which the ultimate substrate of reality is something else entirely. Perhaps a quantum of geometry, perhaps information, perhaps something that has no name yet. What we know, with as much certainty as science can provide, is this. The deeper you look at matter, the less material it becomes. Every experiment designed to find the stuff at the bottom of things has instead found patterns, oscillations, and fields. The last 2,600 years of physics have been a sustained and gradually victorious effort to see through the appearance of solidity and find what is actually there. The answer changes everything and nothing. The rock still sits on the table. It still has weight and hardness and temperature. It still behaves exactly as rocks have always behaved. But what it is, what any of us are, turns out to be something far more extraordinary than anyone imagined when they first picked up a piece of black stone in ancient Greece and noticed that it pulled on iron. A rock is trapped light, so is everything else. What comes next in this investigation is not more experiments of the kind done in the past century. The fundamental particles are well mapped. The standard model is complete, or nearly so. The next step requires probing energies and scales that no current technology can reach, either in particle accelerators, which would need to be many orders of magnitude more powerful than any built, or in observations of the early universe. When those energies existed naturally, gravitational wave astronomy is opening a new window. The detection of gravitational waves in 2015 by the LIGO experiment confirmed that space-time itself is a dynamic medium that it can ripple, carry energy, and distort in response to accelerating masses. This is not just a confirmation of general relativity, though it is that. It is a new tool for observing the universe, allowing us to detect events that emit no light and would otherwise be invisible. Observations of the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, dating to roughly 380,000 years after the Big Bang, continued to reveal the fine structure of the early universe and constrain theories about what happened before and during that period. And experiments at the edge of quantum mechanics are probing the boundary between quantum and classical behavior, asking whether there is a scale at which the wave function stops applying and definite properties emerge, or whether quantum mechanics extends all the way to macroscopic objects and the appearance of classical behavior is an illusion. None of these investigations are likely to return a simple answer. The history of physics suggests that each deeper level of understanding reveals new complexity and new questions. The vortex model of atoms suggested fields could be stable. Quantum mechanics showed that stability required entirely new rules. Quantum field theory explained particles as field excitations, but introduced a new mystery. Why do the fields have the properties they do? Whatever comes next, whatever theory eventually reconciles quantum mechanics with general relativity, and perhaps reveals the deepest nature of the fields themselves, it will almost certainly make the world seem even stranger than it does now. And it will almost certainly show that what we took to be fundamental was, once again, not quite the bottom. The 2,600-year journey is not over. It has barely begun. There is a moment in the history of physics that rarely gets the attention it deserves. It happened in a laboratory in Berlin in 1900, on the last day of October, when Max Planck sat down with his family for dinner and told them he had done something that might shake the foundations of physics. He was not exaggerating, and he was not particularly happy about it. Planck had been trying for months to fix a simple theoretical problem. When a hot object glows, it emits light across a range of frequencies. A piece of iron heated to a dull red emits mostly red and infrared light. Heated further, it glows orange, then yellow, then white. The distribution of light frequencies changes in a predictable way with temperature. Everyone could see and measure this distribution. No one could explain it. The classical theory of heat and radiation predicted that the intensity of emitted radiation should increase continuously as frequency increased. At very high frequencies, ultraviolet, X-ray, gamma ray, the theory predicted that a hot object should emit infinite energy. This was obviously wrong. Hot objects did not vaporize the universe. They cooled down. The failure was so glaring that physicists had a name for it: the ultraviolet catastrophe. Catastrophe, because the equations that had been trusted for decades were producing absurd results at high frequencies. Planck found a way to fix the equations. If he assumed that the energy of oscillators in the hot object The atoms vibrating in the solid could only take on values that were multiples of a basic unit proportional to frequency, the equations worked. The formula fit the observed data perfectly at every temperature and frequency. But the assumption was unphysical. There was no classical reason why energy should come in discrete chunks. Planck thought of it as a mathematical trick, a computational device that gave the right answer without having a clear physical meaning. He spent years trying to derive the formula from more conventional assumptions, hoping the discreteness would emerge as an approximation or an artifact of the calculation. It never did. The discreteness was fundamental. When Einstein came along 5 years later and showed that not just the emission, but the propagation of light was quantized, that light traveled in discrete packets of energy, the implications became unavoidable. Energy was not a continuous fluid that could take on any value. It came in chunks, discrete units. The universe was granular at its most fundamental level. This was the beginning of quantum mechanics. And quantum mechanics changed the question of what matter is made of more thoroughly than anything before it. The reason is that quantum mechanics introduced something that had no classical counterpart: the wave function. In classical mechanics, an object has a definite position and a definite velocity at every moment. You might not know what they are, but they exist. In quantum mechanics, these definite values simply do not exist until a measurement is made. Before measurement, the object is described by a wave function that specifies the probability of finding it at each possible location. Werner Heisenberg formalized this in his uncertainty principle in 1927. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. This is not a limitation of our measuring instruments. It is a fundamental property of nature. Position and momentum are not simultaneously defined to arbitrary precision. The universe itself does not contain the information. This principle has a consequence that seems almost magical. The more tightly you confine a particle, the more precisely you specify its position by squeezing it into a small box, the larger the uncertainty in its momentum, and therefore the more energetic it becomes. A particle trapped in a very small space necessarily has a large uncertainty in momentum, which means it necessarily has a large average kinetic energy. This is why atoms are stable. The electrons in an atom cannot simply fall into the nucleus, as classical electrodynamics would predict. If they did, they would be confined to an extremely small volume the size of the nucleus, and their uncertainty and momentum would be enormous, giving them so much kinetic energy that they would fly out again immediately. The equilibrium position of the electron in an atom, the lowest energy state, is a balance between the electrostatic attraction pulling the electron toward the nucleus and the quantum pressure pushing it outward as it gets too confined. Atoms have the size they have because of quantum mechanics. If the universe were classical, atoms would collapse. Matter as we know it could not exist. The same principle applies at even smaller scales. The quarks inside a proton are confined to a region roughly 1 femtometer across a quadrillionth of a meter. Their confinement gives them an enormous uncertainty in momentum, and therefore an enormous kinetic energy. This kinetic energy, this motion energy from quantum confinement, accounts for a large fraction of the proton's mass. When we say the mass of the proton comes from the energy of the fields inside it, we mean two things. First, the strong force field between the quarks has energy stored in it, like a compressed spring. Second, the kinetic energy of the quarks themselves, their ceaseless quantum motion, their unavoidable restlessness from being confined, adds to the total energy. And since energy and mass are equivalent, this energy is the mass. This is perhaps the most concrete demonstration of Einstein's famous equation, E equals mc squared. It is not an abstract theoretical result. It is the reason protons have the mass they do. It is the reason you have mass. Almost all of the mass in your body comes not from the matter that makes up the quarks, which are nearly massless themselves, but from the energy of the fields and the quantum motion inside those quarks. You are energy in motion, wearing the appearance of stillness. Now let us think about what the discovery of antimatter adds to this picture. Paul Dirac was trying to write a quantum mechanical equation for the electron that was consistent with special relativity. The equations he found in 1928 were elegant, more symmetric than anyone expected, but they had an awkward feature. They had two sets of solutions. One set described electrons with positive energy, which was fine. The other described particles with negative energy, which seemed nonsensical. Dirac struggled with this. A particle with negative energy would have been catastrophically unstable. It could keep emitting radiation and falling to lower and lower energy states without limit. He proposed that the negative energy states were all filled, that there was a vast sea of invisible negative energy electrons, occupying every available state, making further transitions impossible. But if this sea existed, it should have observable effects. An energetic photon could knock a negative energy electron out of the sea, leaving a hole. That hole would appear as a particle with positive energy and positive charge, the opposite of an electron. Dirac initially thought this might be the proton, but the mass was wrong. In 1931, he predicted the existence of a new particle, the positron, with the same mass as the electron, but opposite charge. Carl Anderson discovered the positron in 1932 by observing cosmic rays in a cloud chamber, tracks of particles curving in the direction of electrons, but with opposite curvature in a magnetic field indicating opposite charge. Dirac's prediction was confirmed. This was the first prediction of antimatter, and it came directly from the mathematics of relativistic quantum mechanics. The equations required antimatter to exist. There was no choice in the matter. Today, antimatter is not exotic. It is produced routinely in particle accelerators. Positrons are used in medical imaging every day in positron emission tomography scanners. Antiprotons and antineutrons have been produced and measured. Antihydrogen, a positron orbiting an antiproton, has been created and studied at CERN. And the fundamental symmetry between matter and antimatter says something deep about the nature of particles. Every particle has an antiparticle partner with the same mass but opposite charge. When they meet, they annihilate, converting their combined mass entirely into energy, into photons, into radiation. Matter and antimatter are equal and opposite patterns in the fields. When the patterns cancel, all that remains is the wave. This leads to one of the deepest unsolved problems in physics. Why is the universe made of matter? If matter and antimatter are perfectly symmetric, if the laws of physics treat them equally, then the Big Bang should have created equal amounts of both. Equal amounts of matter and antimatter would have annihilated each other completely within seconds. The universe would contain nothing but radiation. There would be no atoms, no stars, no planets, no life. Yet here we are, made of matter. The universe contains matter. There must have been a tiny asymmetry, a slight imbalance in how matter and antimatter were created that allowed a residue of matter to survive the annihilation era. For every billion matter-antimatter pairs that annihilated in the early universe, there was one extra matter particle. That 1 in a billion surplus is everything we see. Why this asymmetry exists is unknown. Physicists have found small violations of matter-antimatter symmetry in the behavior of certain particles, but not nearly large enough to explain the observed imbalance. Something is missing. Either our understanding of the early universe is incomplete, or our understanding of particle physics is incomplete, or both. The question of the matter-antimatter asymmetry is ultimately a question about why the universe exists at all in its present form. It is one of the most important open questions in all of science. Now consider what all this means when you zoom out to cosmic scales. The universe is roughly 13.8 billion years old. In the first fraction of a second after the Big Bang, the temperature was so extreme that the distinction between radiation and matter effectively did not exist. The energy density was so high that photons were constantly converting into particle-antiparticle pairs and annihilating back into photons. The universe was a seething, undifferentiated soup of energy, in which the boundary between light and matter was blurred to the point of meaninglessness. As the universe expanded and cooled, this equilibrium shifted. The temperature dropped below the threshold required to create the heaviest particles. They annihilated and were not replaced. Then the lighter particles followed. By the time the universe was a few seconds old, most of the matter-antimatter annihilation was done, leaving behind the small surplus of matter that would eventually form everything. For the next 380,000 years, the universe was still too hot for electrons to remain attached to protons. Any hydrogen atom that formed was immediately ionized by the intense radiation. The universe was opaque light, could not travel more than a short distance before being scattered. The cosmos was a glowing fog. Then, as the temperature dropped below about 3,000 degrees Celsius, something changed. Electrons and protons combined stably for the first time. Hydrogen atoms formed throughout the universe in a brief cosmic era called recombination, and suddenly the universe became transparent. Light that had been trapped in the fog was released, free to travel in all directions. That released light is still traveling today. We detect it as the cosmic microwave background radiation, a faint glow of microwave radiation coming from every direction in the sky, with a temperature of 2.7 degrees above absolute zero. cooled from its original 3,000 degrees by the expansion of the universe over the past 13.5 billion years. The cosmic microwave background is the oldest light we can observe. It is a snapshot of the universe at 380,000 years old, when matter and light separated for the first time. The tiny fluctuations in its temperature variations of about 1 part in 100,000 are the seeds from which every galaxy, every star, every planet, and ultimately every living thing grew. The structure of the universe, the web of filaments and clusters and voids seen in galaxy surveys, is a grown-up version of those tiny quantum fluctuations, stretched and amplified over billions of years by gravity. The pattern you see in the large-scale structure of the cosmos is a magnified image of quantum uncertainty in the first moments after the Big Bang. Quantum fluctuations, the unavoidable fuzziness imposed by Heisenberg's uncertainty principle, created small variations in the energy density of the early universe. Those variations grew under gravity. Dense regions attracted more matter and grew denser. Sparse regions lost matter and grew sparser. Over billions of years, the dense regions collapsed into galaxies. The galaxies formed stars. The stars forged heavier elements in their cores through nuclear fusion, then scattered those elements across the universe when they died. The carbon in your body was forged in the core of a massive star that exploded billions of years ago. The iron in your blood came from a stellar explosion energetic enough to create elements heavier than iron, a supernova or neutron star merger. You are made of stellar ash, and that stellar ash is made of fields. The entire history of the universe, from the first fraction of a second to the present moment, is a story about energy organizing itself into increasingly complex patterns. The electromagnetic field, the strong field, the weak field, the gravitational field, these are the canvas and the paint. Matter is the pattern they make. When Maxwell realized that light was a wave in the electromagnetic field, he could not have imagined that this insight would eventually connect to the origin of the universe, the nature of atoms, the mechanism of heredity, and the existence of consciousness. But it does. Every thread leads back to the same tapestry. The rock in your hand is the latest chapter in a story that started with an undifferentiated explosion of energy 14 billion years ago. That energy organized itself according to the rules of quantum field theory into particles and antiparticles, and after the Great Annihilation left a small surplus of matter. That matter, protons and neutrons and electrons assembled into hydrogen and helium under gravity, which collapsed into stars, which fused hydrogen into every heavier element, which were scattered by stellar deaths across space, which condensed into new planetary systems, which, on at least one of those planets, organized into molecules of increasing complexity until something formed that could ask where it came from. You are the universe asking about itself, and the answer, for the moment, is you are light that got lost and forgot how to travel in a straight line. The rock on your windowsill has been on a journey of 14 billion years. Every quark inside it, every electron orbiting those quarks, every field holding them together, traces its existence back to that first extraordinary moment when there was nothing and then there was everything. The rock is not a dead object. It is a knot of ancient energy, patiently waiting for the fields to relax, which they will, eventually. In a cold enough universe, far enough in the future, even protons may be unstable. The strong fields that hold quarks together may, over time, scales unimaginably longer than the current age of the universe, allow those quarks to tunnel out of their confinement and recombine into lighter particles. The proton would decay, the rock would dissolve. The energy would return to radiation, and eventually, to the lowest energy configuration the universe can reach. Whether that final state is something like light freely propagating through empty space, or whether it is something stranger that we cannot currently imagine, we do not know. What we do know is that the distinction between rock and light, between matter and radiation, between stuff and energy, is a temporary one. It exists for a particular range of temperatures and energy densities. In the beginning, there was no distinction. At the very end, there may be no distinction. In between, for a few billion years, the distinction gave rise to chemistry and geology and biology and you, and to a genuinely strange and beautiful question. What is a rock? The answer, as best as physics can currently tell, is this. A rock is a macroscopic pattern in a set of quantum fields. The electromagnetic field, the strong nuclear field, the weak nuclear field, and the Higgs field. The pattern is stable on human timescales because the relevant fields have low-energy stable configurations that correspond to the arrangement of atoms in the crystal structure of the rock. The atoms are themselves stable patterns of field excitations, electrons, and quarks, and the fields between them, arranged in a configuration that is energetically favorable. The mass of the rock is mostly the energy of the strong field inside the protons and neutrons that make up its atomic nuclei. A small fraction of that mass is the quantum kinetic energy of confined quarks. A smaller fraction still comes from the interaction of elementary particles with the Higgs field, and an even smaller fraction comes from the rest mass of the quarks themselves, which is also a consequence of the Higgs field. The solidity of the rock, your inability to push your hand through it, comes from the electromagnetic field. Specifically, it comes from the Pauli exclusion principle, a purely quantum mechanical effect that prevents two electrons from occupying the same quantum state. When you push on the rock, the electron clouds of the atoms in your hand begin to overlap with the electron clouds of the atoms in the rock. The Pauli exclusion principle prevents this overlap, creating an effective repulsive force. You feel this force as hardness. The rock does not touch your hand in any meaningful sense. No electrons actually contact each other. The electromagnetic fields of the atoms push against each other, and that electromagnetic repulsion is what you feel. Every sensation of touch you have ever had in your entire life has been electromagnetic repulsion. You have never actually touched anything. You have felt the fields. This is not a metaphor or a philosophical position. It is what the physics says. The matter in your hand and the matter in the rock never come into contact. The fields do, and the fields are, in the deepest sense we currently understand, all there is. After 2,600 years of investigating action at a distance of asking how forces reach across empty space, the answer turns out to be that there is no empty space. Space is filled with fields, and matter is patterns in those fields. The action is not at a distance. The action is the field, and the field is everywhere. The mystery of the amber stone and the lodestone, which captivated ancient Greek thinkers and puzzled scientists for more than 2 millennia, has been answered. Not just in the sense that we have equations that describe the behavior of electricity and magnetism, but in the deeper sense that we understand, at least in broad outline, what they are. They are geometry. They are the shape of space. They are the fabric of reality organized into patterns that interact with each other according to precise rules. And we, and the rocks, and the stars, and the whole observable universe are patterns in that fabric. The question of what lies beneath the fabric, whether there is a deeper layer, whether the fields themselves are made of something, whether space-time is emergent from something more fundamental, is the question physics is currently working on. String theory proposes that the fundamental entities are one-dimensional vibrating strings, and that the different particles are different vibrational modes of the same string. Loop quantum gravity proposes that space-time itself has a discrete, granular structure at the smallest scales, the Planck scale, roughly 10 to the minus 35 meters, and that the fields emerge from the geometry of this granular space-time. Neither theory has been confirmed by experiment. Neither has been falsified. Both are mathematically sophisticated and physically suggestive. Whether either is correct, and whether a correct theory will look anything like either of them, is genuinely unknown. What is known, with remarkable precision and certainty, is everything from the quantum fields up to the behavior of the largest structures in the universe. The standard model of particle physics, despite being widely acknowledged as incomplete, has been tested to a level of precision that no other scientific theory has ever achieved. Quantum electrodynamics, the part of the standard model that describes the electromagnetic field and its interaction with electrons, makes predictions that have been confirmed to more than 12 significant figures, a level of accuracy equivalent to measuring the distance from New York to Los Angeles to within the diameter of a human hair. This is not the accuracy of an approximation or a simplification. This is the accuracy of a theory that has captured something true about the universe. And what it has captured is this: matter is made of fields. Fields carry energy. Energy is mass. Light and matter are the same thing in different configurations. A rock is trapped light. It took 2,600 years to get here. The journey went through soul, through scent, through fluid, through field, through quantum. Each step was hard-won through experiment in mathematics and imagination. Each step revealed a universe stranger and more beautiful than the step before it. We are not at the end. We may never be at the end, but we are somewhere remarkable on the journey. standing in a place where we can look back at the amber stone and the lodestone and trace the line from them to quantum field theory, to the Higgs boson, to gravitational waves, to the cosmic microwave background. And we can look ahead at the open questions: dark matter, quantum gravity, the matter-antimatter asymmetry, the nature of the wave function, and know that each one, if answered, will reveal a universe even stranger and more extraordinary than the one we currently inhabit. The rock sits on the table. The light falls on it. And somewhere in the interaction between the two, in the quantum fields mediating the electromagnetic force, in the photons bouncing off the electron clouds of the rock's surface atoms and traveling to the photoreceptors of your eyes, in the complex neural processing that turns that electromagnetic signal into a conscious experience of seeing something solid and brown and heavy, the universe is, once again, looking at itself. It has been doing this for a very long time. It will keep doing it for a very long time to come. And every time it does, somewhere in the process, a pattern of trapped light becomes aware of another pattern of trapped light and finds it beautiful. To understand just how strange and how sure we are about all of this, it helps to spend some time inside a particle physics experiment. Not in the sense of crawling through the tunnels at CERN, though that would be remarkable, but in the sense of following what actually happens when physicists probe the structure of matter at the highest energies ever achieved by human technology. The Large Hadron Collider, which sits in a circular tunnel 27 kilometers in circumference beneath the French-Swiss border near Geneva, is the most complex machine ever built. It accelerates protons to within a tiny fraction of the speed of light and then collides them head-on, creating brief fireballs of energy at temperatures and densities that have not existed in the universe since the first moments after the Big Bang. In those collisions, the electromagnetic field, the strong field, and the weak field are compressed into a volume smaller than a proton for a tiny fraction of a second. And in that compression, new particles are created from the energy of the collision. Quarks and gluons fly out. W and Z bosons appear and decay almost instantly into lighter particles. Occasionally, very rarely, a Higgs boson materializes from the compressed field and then decays. Each collision creates a spray of hundreds of particles traveling in all directions. Detectors the size of apartment buildings, containing hundreds of millions of individual sensors, record the tracks of these particles. Computers analyze billions of collision events per second, searching for the rare signatures of interest. This is particle physics. It is extravagant, enormously expensive, and arguably the most precise scientific work in human history. And what it has confirmed, over decades of experiments at accelerators around the world, is that the standard model of particle physics, the theory that describes all the known particles, and 3 of the 4 fundamental forces as quantum fields, is correct to a degree of precision that defies ordinary intuition. Every particle it predicted has been found. Every decay rate it calculated has been measured and confirmed. Every interaction it described has been observed. The Higgs boson, predicted in 1964 and discovered in 2012, was the last missing piece. Its mass, its decay channels, its production rate, all consistent with the prediction. The standard model is not a guess or an approximation. It is a mathematical structure of extraordinary depth that has been tested against reality at every accessible energy scale and found to be correct. If you want to know what a rock is made of at the deepest level currently accessible, the standard model tells you: quarks and electrons held together by quantum fields, organized by the rules of quantum mechanics and special relativity. And yet physicists are not satisfied, because there are things the standard model cannot explain. It cannot explain why there are 3 generations of particles, 3 different copies of the quarks and leptons, each heavier than the last, with no apparent reason for the copies or the pattern of masses. Why is there a muon, a particle that behaves exactly like an electron but is 200 times heavier? Why is there a tau particle, behaving the same way but 17 times heavier still? Nature seems to have made 3 copies of the same template, and no one knows why. The standard model cannot explain dark matter. Whatever dark matter is, it is not described by the standard model. If it were, we would have detected it in particle accelerators. The fact that we have not means it is either very heavy, very weakly interacting, or both. This is a gap in our understanding of matter that applies to more than a quarter of the total matter-energy content of the universe. The standard model cannot explain the accelerating expansion of the universe. In 1998, astronomers studying distant supernovae found that the universe was not just expanding, as had been known since the discoveries of Edwin Hubble in the 1920s, but accelerating in its expansion. Something was pushing the universe apart. This something, called dark energy, makes up roughly 68% of the total energy content of the universe. Its nature is entirely unknown. It may be the vacuum energy of quantum fields, the energy of empty space. But when you calculate the vacuum energy from quantum field theory and compare it to the measured value of dark energy, the prediction is off by roughly 120 orders of magnitude. That is not a small discrepancy. It is the largest discrepancy between theory and observation in the history of science. And the Standard Model cannot explain gravity. General relativity, Einstein's theory of gravity, published in 1915, describes gravity as the curvature of space-time caused by the presence of mass and energy. It is extraordinarily successful at describing gravity at large scales, from planetary orbits to gravitational waves to the expansion of the universe. But it is a classical field theory, not a quantum one. It does not incorporate the principles of quantum mechanics. And at the scales where both theories should apply simultaneously near the centers of black holes, at the Big Bang, the two theories produce incompatible results. A quantum theory of gravity is needed. We do not have one. String theory and loop quantum gravity are the two most developed candidates, but neither has made a prediction that has been tested. This is not a failure of the theories per se. The scales at which quantum gravity becomes important are so small, roughly 10 to the minus 35 meters, that we have no technology capable of probing them directly. But it means that the deepest question, what is space-time, and is it also a quantum field, remains open. Consider for a moment what it would mean if space-time were quantized. If space and time, like energy, came in discrete units. If there were a smallest possible length and a smallest possible time. If the smooth continuous geometry that Einstein described were actually a granular structure at scales far smaller than anything we can currently measure, and if the smoothness were an emergent property that appeared when you averaged over many quanta of geometry, this is what loop quantum gravity proposes. The geometry of space-time is made of loops, tiny networks of quantum structure, and what we experience as the smooth fabric of space and time is the large-scale appearance of an underlying discrete structure, in the same way that the smooth surface of water is the large-scale appearance of an underlying collection of discrete molecules. If this is right, then the question of what the electromagnetic field is, what it is made of, what its substrate is, might be answerable. The field would be a property of the quantum geometry. The excitations of the field would be ripples in the quantum geometry. Particles would be topological features of the loop network. This is highly speculative. Loop quantum gravity makes quantitative predictions about things like modifications to the speed of light at very high energies, and these predictions might eventually be testable with sufficiently sensitive observations of gamma rays from distant sources. But we are not there yet. String theory takes a different approach. It proposes that the fundamental objects are not point particles or loops of geometry, but one-dimensional strings of energy vibrating in a space with 10 or 11 dimensions. Different vibrational modes of the string correspond to different particles. The graviton, the hypothetical carrier of the gravitational force in a quantum theory of gravity, is one of the vibrational modes. So are all the particles of the Standard Model. String theory has produced extraordinary mathematics, including deep connections to pure mathematics that have been surprising and fruitful for both physics and mathematics. But it has not yet made a prediction that distinguishes it from alternatives in a way that can be tested. And the extra dimensions it requires are either curled up into a space far too small to detect or somehow hidden from observation. Whether string theory is the right approach is an open question. Whether any of the current approaches to quantum gravity will prove correct, or whether the right theory will look nothing like what anyone has imagined, is genuinely unknown. What can be said with confidence is that the story of matter is not finished. Each level of description we have achieved has revealed a deeper level waiting beneath it. The atom gave way to the nucleus to quarks and gluons, the particles to quantum fields. Each transition required new mathematics, new conceptual frameworks, new ways of thinking about what exists. The next transition, whatever it turns out to be, will almost certainly require an even more radical revision of our concepts. Perhaps space and time will turn out not to be fundamental. Perhaps the notion of a field will need to be replaced by something else. Perhaps the boundary between matter and geometry will dissolve entirely. What makes physics so remarkable is that this process has not been mere guesswork. Each step has been guided by experiments, by mathematical consistency, by the constraint that the new theory must reduce to the old theory in the appropriate limits. General relativity reduces to Newtonian gravity when velocities are small compared to light and gravitational fields are weak. Quantum mechanics reduces to classical mechanics when the objects are large and the actions involved are much bigger than Planck's constant. Whatever theory comes next must reduce to general relativity and quantum field theory in the appropriate limits. This constraint is enormously powerful. It means the new theory is not free to be anything. It must be consistent with everything we know, while also explaining what we currently cannot. It must reach across all scales, from the quantum structure of space-time at the Planck scale to the large-scale structure of the universe. Finding such a theory is one of the great intellectual challenges of our time. It is also one of the most inspiring, because the history of physics shows that each solution to a great problem has revealed a deeper mystery. The solution to the ultraviolet catastrophe revealed quantum mechanics. Quantum mechanics combined with special relativity revealed antimatter. The Standard Model revealed dark matter and dark energy and the hierarchy problem. Whatever solves the hierarchy problem and explains dark matter will likely reveal something equally unexpected. The universe has proven consistently to be stranger than our best guesses. There is no reason to think it has become less strange just because we have stopped looking. For now, the best answer we have to the question of what matter is this. It is organized energy. It is field excitations with specific geometrical properties that give rise to charge, spin, mass, and all the other properties we associate with particles. At the deepest level we can currently probe, there is no distinction between a particle of matter and a quantum of the field. They are the same thing described from different perspectives. A photon of light and an electron are both excitations of quantum fields. The photon is an excitation of the electromagnetic field. The electron is an excitation of the electron field. They interact by exchanging energy and momentum through the electromagnetic field. The process we call light bouncing off a surface is a vast number of these interactions happening simultaneously, photons from the light source being absorbed and re-emitted by electrons in the surface atoms, changing direction in the process. The rock reflects light because the electromagnetic field of the rock's surface electrons and the electromagnetic field of the incoming photons interact in a way that sends most of the photon energy backward. The specific frequency of light that gets reflected determines the color we perceive. The specific quantum transitions available to the electrons in the rock's atoms determine which frequencies are absorbed and which are reflected. Quantum mechanics determines the color of everything. When you look at a rock and see it as brown or gray or red, you are experiencing the quantum mechanical structure of iron atoms and silicon atoms and oxygen atoms, encoded in the frequency of reflected electromagnetic radiation, decoded by the cone cells in your retinas, processed by your visual cortex into a conscious perception. The color is information extracted from the quantum fields. Everything you have ever seen, heard, touched, tasted, or smelled is quantum field interactions all the way down. Your entire experience of reality is constructed from the behavior of fields. The sensations, the colors, the solidity, the warmth. These are all the result of electromagnetic field interactions between the atoms in the world and the atoms in your sensory organs. This does not make the experience less real. It makes it more astonishing. You are a pattern in the quantum fields that has become complex enough to experience other patterns in the quantum fields and find them beautiful, alarming, delicious, painful, or boring. The relationship between the pattern and the experience between the physics and the consciousness is the deepest mystery of all. We have no theory of consciousness. We do not know why there is something it is like to be a brain processing information from the fields, rather than just information processing happening in the dark. But whatever consciousness is, it is happening in a universe that turns out to be made of something far more elegant and strange than anyone expected. A universe where the line between matter and energy dissolves at high temperatures, where rocks and light are the same thing at different energies, where empty space seethes with quantum fluctuations, where the smallest things have no position until you look at them, where the act of observation is, in some sense, woven into the fabric of reality. After 2,600 years of asking what matter is, we have an answer that is both more precise and more mysterious than anyone who first held a lodestone in their hand could have imagined. The precision is in the mathematics, in the equations of quantum field theory that predict experimental outcomes to 12 decimal places. The mystery is in the implications in what it means that fields are the fundamental substrate, that mass is energy, that observation plays a role in the nature of physical reality. We know what a rock is made of. We do not know what that knowing means. And that, perhaps, is the most remarkable thing about 2,600 years of physics. It has not simplified the universe. It has revealed it to be more interesting than it had any right to be. The amber stone that attracted feathers, the lodestone that pulled iron, the compass that twitched when Ørsted connected his battery. These were not puzzles to be solved and then shelved. They were doorways, and each doorway led to a larger room with more doorways. We are still walking through them. We will be for a very long time. There is a particular experiment that physicists sometimes call the most beautiful in science. Not because it produced a Nobel Prize, not because it overturned a theory, but because it demonstrates the absolute strangeness of quantum mechanics in the most direct and undeniable way possible. It is called the double-slit experiment, and you can do it with a single electron. Fire a single electron at a barrier, with 2 narrow slits cut into it. Behind the barrier, place a detector that can record exactly where the electron lands. Do this over and over, 1 electron at a time, and watch the pattern that builds up. If the electron were a classical particle, a tiny billiard ball, you would expect it to pass through one slit or the other, and the distribution of landing positions would be 2 clusters, one behind each slit. That is what intuition predicts. That is what makes physical sense. What you actually see is an interference pattern, alternating bright and dark bands, exactly the pattern you would get if the electron were a wave spreading through both slits simultaneously and interfering with itself. Bands of high probability where the 2 waves add together. Bands of 0 probability where they cancel. But the electron is detected at a single point. It is not smeared out. It arrives in one place. And yet the distribution of arrival points the accumulated result of thousands of individual electrons, each arriving at a single location, traces out a wave interference pattern. This can only mean one thing. Before the electron was detected, it was in a superposition, a genuinely quantum state, in which it passed through both slits simultaneously and interfered with itself. The interference pattern is not statistical. It is not the result of some electrons going through the left slit and some through the right. It is the result of each individual electron going through both slits at once. If you close one slit, the interference disappears. The electron can only go through one slit, and the interference pattern vanishes. This is not because the electron decides to go through only one slit when you close the other. It is because the act of making one slit unavailable changes the quantum state of the electron and eliminates the possibility of interference. Now add one more twist. Put a detector at the slits to determine which slit each electron goes through. You might think this would not affect the pattern. Surely you can just watch without disturbing anything. But the instant you have a detector that can, in principle, tell you which slit the electron went through, the interference pattern disappears. Even if you never look at the data from the detector, even if you delete it before reading it, the mere fact that the information exists destroys the interference. This is the measurement problem at its most vivid. The quantum state changes when information becomes available. Not when the information is read, but when it could in principle be read. The boundary between possible and actual, between quantum superposition and definite outcome, seems to depend on information on whether the universe has kept a record. What this means about the nature of reality is genuinely contested among physicists and philosophers. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, says that quantum mechanics describes our knowledge of a system, not the system itself. The wave function is not a physical wave. It is a tool for calculating probabilities. Questions about what the electron was doing before we measured it are meaningless. There is no fact of the matter. The many worlds interpretation, proposed by Hugh Everett in 1957 and subsequently developed by others, says that the wave function is physically real, and when it appears to collapse, it does not actually collapse. Instead, the universe splits. Every possible outcome occurs in a separate branch of the wave function. When you detect the electron, you, or rather, a copy of you, exists in a branch where the electron was detected at that location. Another copy of you exists in every other branch, in each of which the electron was detected somewhere different. Reality is an ever-branching tree of parallel worlds. The pilot wave interpretation, developed by Louis de Broglie and later extended by David Bohm, says that the electron is a real particle with a definite position at all times, but it is guided by a pilot wave that passes through both slits and produces the interference pattern in the probability distribution of where the particle lands. This interpretation is deterministic given the initial conditions. The outcome is fixed. But the pilot wave is non-local in a way that makes many physicists uncomfortable. These are not the only interpretations. There are many others, each with its own strengths and difficulties. What they all have in common is that they are consistent with every experimental prediction of quantum mechanics. The predictions are the same. Only the ontology, the story about what is actually happening, differs. This is a remarkable situation for science to be in. We have a theory of extraordinary precision and predictive power, and we do not agree on what it means. We can calculate what will happen with astonishing accuracy, but we cannot tell a single coherent story about why it happens. This is not a failure of science. It is science working exactly as it should, reaching the edge of where current concepts apply and signaling that new concepts are needed. The history of physics is full of these moments. Newtonian mechanics worked perfectly for 2 centuries until relativity and quantum mechanics showed that its concepts of absolute time and definite particle trajectories were approximations valid only in certain regimes. Perhaps quantum mechanics itself is an approximation. Perhaps the wave function is not fundamental but emergent from something deeper. Perhaps the measurement problem will dissolve when the right deeper theory is found. Just as many paradoxes of classical physics dissolved when quantum mechanics replaced it. The physicist John Wheeler, who worked with Bohr on the theory of nuclear fission and later coined the term black hole, spent the last decades of his long career thinking about the foundations of quantum mechanics. He came to believe that the universe was fundamentally about information, that bits were the underlying substrate from which space-time and matter and everything else emerged. He called this vision "it" from bit. In Wheeler's picture, asking what matter is made of is the wrong question. The right question is what information is matter made of. A particle is not a thing. It is an answer to a question. And the universe is in the business of asking and answering questions at every point in space-time, building up the appearance of a continuous material world from a vast web of binary distinctions. This is deeply speculative, but it is not empty speculation. Ideas descended from Wheeler's "it from bit" vision have become important in theoretical physics through the study of quantum information, the holographic principle, and the AD-CFT correspondence. The holographic principle, proposed by Gerard 't Hooft and later developed by Leonard Susskind, says that all the information in a volume of space can be encoded on the surface surrounding that volume. The 3-dimensional interior is redundant with the 2-dimensional surface. The universe might be, in some sense, a hologram, with the physical world we experience being a projection of information encoded on a higher dimensional boundary. The AD-CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete mathematical realization of this idea. It shows that a quantum gravity theory in a curved space is mathematically equivalent to a quantum field theory on the flat boundary of that space, with one fewer dimension. Gravity emerges from the quantum entanglement structure of the boundary theory. Space-time itself is built from quantum information. This is not just a theoretical curiosity. The AD-CFT correspondence has become one of the most powerful tools in theoretical physics. It has been used to study strongly interacting systems like the quark-gluon plasma created in heavy ion collisions in situations where ordinary perturbation theory fails. It has provided insights into black hole thermodynamics. It has suggested deep connections between gravity and quantum information theory that were not anticipated. Whether it describes our actual universe, which does not appear to be an anti-de Sitter space, is still unclear. But it has profoundly changed how physicists think about the relationship between gravity, space-time, and quantum mechanics. The recurring theme in all of this, from Maxwell's field to quantum field theory to the holographic principle, is that the things we thought were fundamental turn out to be derived from something more fundamental. The field seemed fundamental until it was quantized. The quantized field seemed fundamental until we realized it might emerge from entanglement in a quantum information structure. The space-time that fields live in might itself emerge from quantum correlations. Each layer of explanation is real and useful and accurate within its domain. Classical electrodynamics correctly describes the behavior of electromagnetic radiation and matter at everyday scales. Quantum electrodynamics extends this to atomic and subatomic scales with extraordinary precision. Quantum field theory describes all the known particles and forces except gravity. What comes next will extend the description further into regimes we cannot currently access. At every scale, the pattern is the same. What appears to be solid, discrete, and material dissolves on closer inspection into something more fluid, more relational, more dynamic. The rock is atoms. The atoms are mostly empty space threaded by quantum fields. The fields are excitations of an underlying quantum structure. The quantum structure may be built from information. And at the end of all that unpacking, the question of what information is what it ultimately means for two physical systems to carry information about each other, and what this has to do with the physical world we experience might turn out to be the deepest question of all. Deeper than what is matter made of. Deeper than what is time. Perhaps even the question from which all other questions derive. For the ancient Greeks, who first rubbed amber with fur and watched it attract feathers, the question was simple. Why does that happen? The answer has led, over 2.5 millennia, to a picture of a universe so strange that no one would have been able to imagine it in advance. A universe where the vacuum seethes with invisible fluctuations, where observation affects reality, where space-time might be a hologram built from quantum entanglement, where the mass of a rock is mostly the energy of strong fields inside protons that are themselves mostly empty space. None of this makes the rock less solid. It sits on the table exactly as it always has. Its weight, its texture, its temperature, its color, all of these are real. But what they are, what they consist of, has turned out to be the most improbable and extraordinary answer to the most ordinary question. The question was, what is this? The answer? After 2,600 years of trying, this is light that has forgotten how to move. That answer is partial. It describes what matter is within the framework of quantum field theory. It does not explain why the fields exist, why the constants have the values they do, why there is something rather than nothing, or what the quantum fields are made of at the deepest level. It does not tell us whether the holographic principle is correct, or whether it from bit is the right way to think about the foundations of physics, or what a quantum theory of gravity will ultimately look like. But it is true within its domain, and its domain is everything we have ever touched. The experiments continue. The Large Hadron Collider runs, looking for signs of physics beyond the standard model. Gravitational wave detectors look for signals from neutron star mergers, black hole collisions, and possibly cosmic strings or phase transitions from the early universe. Space telescopes map the distribution of dark matter through gravitational lensing of distant galaxies. Underground detectors look for direct evidence of dark matter particles interacting with ordinary atoms. Quantum computers implement quantum field theory calculations that no classical computer could approach. The picture gets sharper every decade. The mysteries get deeper. The universe keeps revealing new layers, each one more astonishing than the last, each one suggesting that what lies beneath is even stranger. This is what makes physics different from other ways of knowing. It does not just confirm what we already think. It actively undermines our intuitions, dismantles our assumptions, and replaces them with something true, but often deeply counterintuitive. It does not comfort us with familiar stories. It invites us into a world that is, on inspection, nothing like what it appears to be from outside. The amber stone, the lodestone, the twitching compass needle, the spark across the room, the electron producing an interference pattern with itself, the photon that becomes an electron and a positron, and then becomes a photon again, the proton whose mass is almost entirely energy. Each of these is a window into the same reality. A reality that looks, from our scale, like a world of solid objects interacting through forces. A reality that looks, from the atomic scale, like mostly empty space, threaded by quantum fields. A reality that looks, from the subatomic scale, like excitations in those fields dancing according to precise quantum rules. A reality that looks, from the deepest level we can currently probe, like information all the way down. And at the human scale, where we actually live, none of this changes anything about the experience of picking up a rock. It is still heavy, it is still cold, it is still real. It is just also, at the same time, trapped light. To close the loop on everything we have covered, It is worth dwelling on one particular experiment that bridges the ancient question and the modern answer more vividly than almost anything else. It is an experiment you can conceptually hold in one hand. Take a piece of glass, heat it until it glows. Look at the light it emits. Pass it through a prism. You will see a continuous spectrum of color every shade, from deep red through orange and yellow, and green and blue to violet. This is the thermal emission spectrum of a hot solid. It was the object Planck was trying to explain in 1900. Its shape, the characteristic hump of intensity, rising to a peak and falling off, depends only on temperature, nothing else. Now take a glass tube, fill it with hydrogen gas, the simplest element, one proton, one electron, and run an electric current through it. It glows, but this time the light is not a continuous spectrum. Pass it through a prism, and you see 4 bright lines. One red, one cyan, one blue, one violet, nothing in between. A series of precise frequencies. The hydrogen emission spectrum. These 4 lines are the same wherever you look in the universe. The red smear of glowing hydrogen in a distant nebula shows the same 4 lines. The spectrum of a star a billion light years away shows hydrogen absorbing light at exactly these frequencies. Hydrogen in a laboratory on Earth and hydrogen in a galaxy 10 billion years old carry the same spectral signature. Why exactly those 4 frequencies? Why not 3, or 7, or a continuous smear? This question stumped 19th century physicists completely. They could measure the frequencies precisely. They could see that the numbers followed a mathematical pattern called the Balmer series, after the Swiss mathematician Johann Balmer, who found the formula in 1885. But no one could explain why the formula worked. Why those specific numbers? The answer, when it came in 1913 through the work of Niels Bohr, was the first major clue that something deeply quantum was happening inside atoms. Bohr proposed that the electron in a hydrogen atom could not orbit the proton at any arbitrary distance. It could only occupy certain specific orbits, each corresponding to a specific energy. When the electron jumped from a higher orbit to a lower one, it released the energy difference as a photon. When it absorbed a photon of exactly the right energy, it jumped to a higher orbit. The 4 lines of the hydrogen spectrum corresponded to 4 different transitions, 4 specific jumps between specific energy levels. The frequencies of the emitted photons were determined by the energy differences between levels, and those differences were fixed by quantum mechanics. This was the first time quantum mechanics directly predicted something about the structure of atoms and was confirmed. Bohr's model was too simple. It only worked exactly for hydrogen, but the idea was right. Energy levels in atoms are quantized. Electrons can only be in specific states. Transitions between states produce or absorb photons of specific frequencies. The full quantum mechanical theory, developed over the following decade, explained not just hydrogen but every element. The periodic table, the organizing structure of all chemistry, is a consequence of quantum mechanics. The number of electrons each element can hold at each energy level, the way they fill those levels following Pauli's exclusion principle, the chemical bonds formed by sharing electrons, all of it follows from the mathematics of quantum mechanics applied to electromagnetic fields. Chemistry is quantum electrodynamics. Every chemical reaction that has ever happened, every bond formed, every molecule built, every reaction run, in every cell of every living thing since life began, has been a quantum mechanical interaction of electrons in electromagnetic fields. Life itself is organized quantum field interactions. The DNA molecule that encodes your genetic information is held together by quantum mechanical bonds between atoms. The proteins that carry out every function in your cells are assembled through quantum chemical reactions. The enzymes that catalyze those reactions exploit quantum tunneling, a phenomenon with no classical analog, in which a particle passes through an energy barrier that classical physics says it cannot surmount. Quantum tunneling in enzymes is not a side effect or a curiosity. In many cases, it appears to be essential to the reaction rate. Without quantum tunneling, key biological reactions would happen too slowly to sustain life. The chemical machinery of life runs on quantum mechanics. Even the sun's energy production depends on quantum tunneling. At the temperatures and pressures in the solar core, classical physics predicts that 2 protons cannot get close enough to fuse. The electromagnetic repulsion between them is too strong. But quantum tunneling allows protons to pass through the barrier and undergo nuclear fusion at rates sufficient to power the sun. Without quantum tunneling in the sun's core, there would be no sunlight. Without sunlight, there would be no photosynthesis. Without photosynthesis, there would be no complex life. The rock sits in sunlight. The sunlight comes from quantum tunneling in the solar core. The rock's color, the specific frequencies of light it reflects, comes from quantum transitions in the electron shells of its atoms. The chemical bonds holding it together are quantum mechanical. The nuclear forces holding its atoms together are quantum field interactions. The rock is quantum mechanics all the way through. And the sun, the rock, the air, the grass, the person holding the rock, all of these are the same fields in different configurations. The electromagnetic field is everywhere. The strong nuclear field is everywhere. The Higgs field is everywhere. The electron field, the quark fields, all the fields of the Standard Model, they permeate every point in space. What differs from place to place is the excitation pattern. Here, the fields are in a low-energy background state, empty space. There, they are excited into the configuration we call a proton, containing 3 quarks glued together by gluon field excitations. Assembled into nuclei, surrounded by electron field excitations, bound into atoms, arranged in molecular configurations, packed into crystal lattices, and we have a rock. The fields are always there. What changes is the pattern they make. And the patterns, on the scale of atomic nuclei, are held together by binding energies equivalent to enormous amounts of radiation. Split the nucleus and the energy is released. This is nuclear fission, the same energy that powers nuclear reactors and nuclear weapons. The mass of the split fragments is slightly less than the mass of the original nucleus. That small mass difference, multiplied by the speed of light squared, is the energy released. Mass becoming energy. Energy becoming light. The same equivalence that makes a rock a form of trapped light, running in reverse. Fuse 2 nuclei together, and even more energy is released, because the binding energy of the fused nucleus is greater than the sum of the binding energies of the original nuclei. The fused nucleus is slightly lighter. That mass difference becomes energy. This is nuclear fusion, the process that powers the sun, and the process that created every element heavier than hydrogen in the nuclear furnaces of stars. The rock you are holding contains iron, silicon, oxygen, magnesium, calcium, and dozens of other elements in trace amounts. Every atom of every element heavier than hydrogen was forged in a stellar nuclear reaction. The iron in the rock was created in the core of a massive star in the final moments before it exploded. The silicon came from carbon and oxygen fusing in an intermediate mass star. The oxygen came from helium burning in earlier generations of stars. Before those stars existed, the universe contained only hydrogen and helium, created in the first few minutes after the Big Bang. Everything else was forged later, by the process of stellar nucleosynthesis, guided entirely by the same quantum field interactions that govern everything else. You are looking at the exhaust from 10 billion years of stellar nuclear physics. The rock on your windowsill is a record of the nuclear history of the galaxy. And the nuclear history of the galaxy is a story about fields. About the strong field confining quarks into protons and neutrons into nuclei. About the energy stored in those configurations and released when they rearrange. About the electromagnetic field, carrying that energy across space as light, which eventually falls on planets and drives chemistry and powers life. The sun shines because of the fields. The rock forms because of the fields. You live because of the fields. And you ask about the fields because of the fields. Everything connects. The amber stone and the universe's expansion. The twitching compass and the quantum nature of space-time. The 4 lines of hydrogen spectrum and the nuclear furnaces of dying stars. 2,600 years of following threads, and every thread leads to the same place. There are no things. There is only the field, and we are its most interesting excitation. The amber stone has waited 2,600 years for this answer. It still sits in a museum in Athens, drawing no visitors. The lodestone still pulls on iron, as it always has, obeying Maxwell's equations to the letter, indifferent to whether anyone understands why. The compass still points north, because a trillion electrons in the Earth's iron core are lined up in the same direction, their quantum spins aligned, their tiny magnetic fields, adding into a planet-scale field that reaches up through the crust and atmosphere and guides every needle that has ever been trusted to find the way home. Physics did not diminish the wonder of these things. It increased it. The more precisely we know what these phenomena are, the more remarkable it becomes that they exist at all, that a universe can make fields, and that those fields can fold back on themselves and become curious about the folding. The question that started this, how does movement become a rock, has an answer now, at least an outline. Movement becomes structure when the fields are shaped right. Structure becomes mass when the fields confine enough energy in a small enough volume. Mass becomes you when the structure is complex enough to process information about itself. And you become curious when the structure starts asking where it came from. This is what physics is. It is the field asking about the field. It is light trapped in a rock-shaped loop, trying to remember what it was before it got caught.